Hi, next is the Poisson convolution. Let again x and y be independent. X of Poisson lambda distribution and y of Poisson mu. They're independent. And we want to find again the distribution of x plus y. So the mass function of x plus y at k, clearly the Poisson is non-negative integer, this sum is non-negative integer, so take k to be non-negative integer. It's the sum from minus infinity to infinity, mass function of x at k minus I, mass function of y at I. Now let me put in the mass functions. So x is Poisson lambda, so this is going to be lambda to the k minus I over k minus I factorial e to the minus lambda. Y is Poisson mu, so this is going to be mu to the I over I factorial e to the minus mu. But at this point I have to be very careful, because these formulas are only true for non-negative parameters here, non-negative variables here, I or k minus I. So I cannot be negative, so I'm not allowed to go negative with this sum anymore, because then this part wouldn't be true. And k minus I is not allowed to be negative, so I'm not allowed to go above k with my summation index I, otherwise k minus I would go negative, and this thing is not that thing when k minus I is negative. Okay, so this is now really I equals to 0 to k. This is now really a finite sum, and I really have to respect that with the boundaries if I write those formulas in for the mass functions. Okay, so how do I sum something like that up? First of all, notice that the exponentials are not dependent on I, so I can factor those out. What is left is something to the I, some other thing to the k minus I, and actually I factorial and k minus I factorial are pretty much the important parts of a binomial coefficient. So I'm going to write out e to the minus lambda and e to the minus mu collected together in this form, e to the minus lambda plus mu. I am actually going to write a sum from 0 to k of k choose I, and that will have the k factorial on top, which is not present in the formula before, so I'm going to make up for that by dividing with it, but it will have the I factorial which is there and the k minus I factorial which is there. So this k choose I binomial coefficient was almost there except for the k factorial. And then I have the mu to the I and the lambda to the k minus I, still in my sum in the previous version. And from here it's very easy, e to the minus lambda plus mu over k factorial stays there. And then this thing, according to Newton's binomial theorem, is the sum of mu plus lambda to the k. I have all the terms I need. I have k choose I have mu to the I have lambda to the k minus I. That's exactly what Newton binomial theorem is about. Summing up k choose I, something to the I, some other thing to the k minus I, is the sum of those two terms to the k's power. And so that's what I'm going to put in here. Lambda plus mu or mu plus lambda, doesn't matter, to the k, in which we actually read off the mass function of a Poisson random variable of parameter mu plus lambda at value k, and that proves, since this is true for all non-negative k, that proves that x plus y is actually Poisson mu plus lambda. So the conclusion is that x plus y is Poisson mu plus lambda, or a slightly different notation is that Poisson lambda convolved with Poisson mu is Poisson mu plus lambda or lambda plus mu, doesn't matter. Okay, now Of course, if you know where Poisson comes from, it comes from a limit of binomials, and we're going to prove that later on. If you know that, then of course you can pass the limit through the sum of independent random variables, and you can directly conclude this from the convolution formula for binomials, which I did in the previous video.